Hello and welcome to Extreme Academy Live. This is where you come to advance your knowledge, advance your skills, and advance your future. So this is free of charge technology training from Extreme Networks. So everything's free in terms of the lessons. You can then take an exam at the end of the course. That gives you a certification from Extreme Networks. You can put that on your CV and it can help you advance your career. And you've been telling us that's been happening for you. So we talked about Ramadan last week. And this week, I want to give a shout out to Ryan. So Ryan, if you're out there, if you're watching, then thank you for sending us in that letter. We sent it around to some of the team here and some of the executives here at Extreme. I hope you don't mind. We shared what you said about how you're advancing as a result of Extreme Academy. So big shout out to you. Well done on advancing your career. And I think you're going to be involved in some of our social media coming up. So everybody look out for Ryan's story at some point when it hits our social media feed. All right, so short intro from me today because we've got a lot to cover. Last week we covered the business side, the business side of designing a network. So talking about the business outcomes you're trying to achieve and what's important in different use cases and use cases of retail, hospitality, stadiums, etc., etc. Now that stuff, that's the sort of stuff you should have in your mind when you go for a job interview. So if you've got a job interview coming up or you have one next year at some point, I recommend go back and watch that episode because you'll pick up some of the language. And it was all those words with ility in the end, manageability, scalability, flexibility. It's all the buzzwords that you probably need to be using when you're in an interview, and it'll show the person who's interviewing you that you understand, the business outcomes, the business side of IT, and the outcomes that are probably facing the person, the challenges that are facing the person you're interviewing with. So if you know that stuff, and if you're using those words and you're talking that language, you're going to do really well in that interview. Right, so this week we've got a lot to cover. We're getting more into the technology and design considerations. So I can see Isaac. Isaac, I'm going to leave you to talk about how to ask questions, how to engage. So you cover that. Yep, he's nodding. I'm going to throw you a surprise one week, Isaac, just to because we rehearsed this, but I think I might give him a surprise one week. Isaac's going to cover that. The thing I wanted to mention was just make sure, and I think you all know this, but immediately that these live streams finish, the recording is posted. It's like almost instantly. That's a great thing about YouTube. So you can, if you have to step away, these are long lessons that, 2 hours. If you have to step away, if you can't stay for the whole thing, then they just come back later. You can just pick it up later. And looking at this week's content, I think we've got a lot to cover. So sometimes we run in early. Sometimes we're dead on the 2 hours. I think this week we might be just looking at the amount of content Isaac's going to cover, I think we might run a little bit late. So if that happens, and if you have to go at the top of the hour, you've got another appointment, another lesson or meeting to go to, that's fine. Just go to that, and then just know you can come back to YouTube anytime and pick up the rest of it. When Isaac gets going, we don't like to interrupt him, and sometimes even when we do try to speed him up, he ignores our messages. So so it can happen. So hope you think that's okay. If you can stay to the end when we run a little bit late, then that'd be great. Just stick around with us. So towards the end, we might put a message in the chat if we can see. We can roughly guess when we're going to finish based on the slide that we can see Isaac is on at any moment. All right, Isaac, you ready? Okay, he's nodding. Let's hand it over to Isaac. Enjoy lesson 2.
Being able to teach is one of the greatest privileges that anybody can have. I'm in the very fortunate position of being able to do that, and not only that, to actually love what I'm doing. Let me just set my clock over here. So thank you, Rowan, for that introduction. Thank you for the team that makes Extreme Academy just run. Believe me, it looks smooth when you watch this. It just kind of flows really nicely. All the pieces fall into place. But if it wasn't for Claire and Bethany and Rowan and other people behind the scenes, it would be a lot more difficult. If you haven't watched any episodes before of Extreme Academy, this is just our program that we do absolutely free of charge, as has been mentioned before. It's not one of those where you get the lessons free and you have to pay for the exam or something. It's not like that. Everything is free, 100% free. I mean, you're watching this, you didn't even have to register. We asked you, but you didn't even have to register to watch this live with online support, or even to watch this on demand. But of course, if you at the end of this, if you want to go for your certifications, and you should, then we're going to need an email address, kind of, so that we can send you a certification and send you the link and the URL for you to go and get the exam. But welcome. Thank you for attending these courses. The numbers that we get of people watching online are really fantastic. Last week was the anniversary, the 1-year anniversary of Academy, and we've come such a far distance in simply 1 year. Our LinkedIn profiles, our YouTube channels, the amount of views that we've got has really been so encouraging for us, because ultimately that's what we wanted to do with this. We wanted to help you change careers, grow in your careers, and even those people who might not be networking engineers but kind of want to know and understand, what is networking all about? How does it actually work? To all of you, welcome. And I've said this before as well. If you know all this stuff, and we got some really smart people, in the back office just answering your questions, and even on the chat. We've got some highly qualified people. We got some moderators from Discord. You look at these guys' CVs, they are so experienced, so smart. And so we got a lot of people who can answer questions. But if you're one of those and you know all of this stuff, hey, don't look at this and say, oh, it's not on that level or whatever. It's not university. It's not designed for that, right? It's not designed for that. But don't go away. Don't feel, oh, this is, help someone else. Stick around, listen, watch, learn something maybe. I don't know. Maybe I can teach you something. I don't know. But learn and help other people. Help other people. Remember, I've spoken about Discord before. If you haven't joined our Discord channel, Claire will put the URL. Claire, if you don't mind, put the URL up on screen for 10 seconds or 15 seconds, whatever, using the QR code. You can just take your mobile phone. You can, go to the photo app and just point it at there, and it will automatically detect that. And then you can go and sign up and join our Discord community. We've got a number of moderators on there. We're always looking for more, especially female. We don't have any females yet. Hey, girls, what's happening? Come and join us on the Discord channel. And any questions that you have that are not answered right now on the YouTube chat, which is, I think that side, any questions that are not answered now, feel free to go take them to the Discord channel and ask them there. And we will try and get an answer for you, or an explanation. We wanted to make Discord a safe place for anybody from any level to be able to ask questions. There's no such thing as stupid questions. I hate it when people say, I want to ask you a stupid question. It's not a stupid question. The only question that kind of feels stupid is the one that you don't ask, and then you walk away not really knowing. So if you hear an explanation, if you hear me teaching something here, I can't really stop to go and answer questions, and because there's a lot of people watching, right? But if you want to ask a question, maybe you're shy, you don't want to ask it on the chat because you think, oh, people will think I'm silly or not. They won't. But if you feel that they're going to do that, then rather go to Discord and ask it there. I have been very clear with the moderators, and I've said that Discord channel is a place, a safe space for people who don't know, or who want to know, or want to ask. If you have a question you think it's really silly, or no one, go there and ask it. And if you don't get it first time, ask again. Don't be shy. There will be somebody there who will help you, because that's what we're here for. We're here to help you and to help you grow and advance in your career, as Rowan said at the beginning. So last week we started by talking about not so much bits and bytes, but more the thinking, I want to say kind of the philosophical approach to building networks, right? Why do we build networks? When Extreme, talks about building networks, why do we have these processes in place? Why do we make the kind of recommendations that we do? Why do we, go through the stuff that we showed you last week? And that's because ultimately it's all about business objectives, right? All of you watching over here are probably employed or want to be employed in this industry or possibly other industries. And part of being employed in the networking industry is understanding terminology, understanding the philosophy of why do you do it this way. And it's essentially to achieve business outcomes. And we spoke about those last week. If you haven't, I'm not going to go over that, but if you didn't watch last week, go and watch it, because we talk about these things, about resiliency and redundancy and all of these. And we used a use case right at the end about esports, this growing things. Really, it's growing massively around the world. In the US, it's probably growing faster than most places. But we're kind of going to use the example of the esports thing as we go through everything. And as we landed last week, we were talking about specifically things like ping times and things like that. And when you think about that and how it relates to esports, like, it doesn't matter how good you are as a gamer, how fast reactions you actually have, how quickly you can manipulate that controller. Ultimately, those manual actions need to be translated into digital actions and carried across the networking. And if you have a high RTT, if you have high ping values, if you have a high lag, then all of this that you do here is going to result in a poor experience on there. And so we saw, just in something simple, not even stock exchange trading, but in gaming, how having a network experience that meets business objectives is so important, because ultimately it determines the quality of the experience that you as a gamer enjoy. So let's jump in, and as I normally do, for those of you who don't know, I got an iPhone in front of me. I record everything on iPhone. Microphones here. I normally have a tablet. I have a clock and a monitor. I can see clear and all sorts of stuff, and I have this big screen in front of me. So sometimes when I want to be very specific, I have to look at the screen and read some stuff. This is not teaching by PowerPoint. I do use PowerPoint, but sometimes I have to read off screen. And so we're going to look at when we build for business objectives, what are the learning objectives for this? Well, we're going to learn about the different types of control planes that you get, or different planes that you get. We're going to get one slide that talks about the OSI model as a refresh. We're going to look at Ethernet, right? We're going to look at Ethernet, because that really has been the basis of carrying packets around the world for the last 75, 25, 45, 46 years already. We're going to look at loops, layer 2 loops, and that's an interesting one. Then we're going to go look at routing choices, redundancy, and the impact on convergence. We'll cover that. It's a really nice word, convergence. We'll cover that. And then we'll look at quality of service and the impact on RTT regarding latency, jitter, and things like that. And again, related to esports. So we'll carry that whole esports story all the way through. Right. So every network device, every network system has to perform at least three distinct activities, all right? Every network device, a switch, an access point, core switch, edge switch, whatever, they have to perform at least 3 key activities. And now we're going to find out what are those 3 activities that they have to do, and also where are those activities actually executed. Okay, are we talking about cloud execution, or are we actually talking about local execution, on-prem type of execution? Those are interesting questions. Now, this is what we're going to be talking about. We're going to be talking about the different planes. Now, planes, not as in aeroplane, and plain not as in like chocolate or plain vanilla. No. We're not talking about that. We refer to it, for those of you who are not, natural first language English speakers, planes, think of it almost as domains, different domains. It's not domains, but it's kind of domains. So 3 separate domains, 3 separate planes that we're going to be talking about. Network management plane or domain, control plane, or data activity plane, domain. Okay, those 3.
Sorry, could you say that again? Sorry, I couldn't hear what you said.
It's okay. It doesn't matter if you can't hear what I said. My watch sometimes does stuff like that. So let's address the first part, which is management plane. Management plane. This is where the network interacts with its administrator. Okay, the administrator could be a human being, or a human being that is controlling a system that is managing. Ultimately, the administrator or administrators. And they do this through the management plane, management domain, management level. So it's almost always, yes, always an application focused on managing the device. Now, already in Extreme Academy, we are not we are brand agnostic. We're not here to sell Extreme networks. I'm also not here to sell Cisco also, but I know that they also exist and they're a massive player. But we like to talk about technologies. But in this case, I'll refer to Extreme Cloud IQ because it's one of the products that we sell that manages and that fits into this management plane. When I talk about management plane, Extreme Cloud IQ is this application, like you see there, that you access by going onto a browser. And within that application, you can set up, you can configure devices, you can take an access point, you can take a device like this, and you connect it up to the cloud, and from there you can then manage it, you can configure it, you can optimize it, you can fine-tune it. If you've got an access point, you're like, okay, take that 6 gigahertz antenna and use that for, as a monitor, as a scanner, then use the 5 gigahertz for this and use the 2.4 for that. That's the type of stuff that we mean when we say, optimize, fine-tune, troubleshoot. That's the plane. On the management plane, that's where you would ask questions like, how good is my network? Am I finding a lot of am I finding a lot of errors? Is there a lot of unauthorized access points on my network? That's the place where you find reports, where you run reports and you start to understand, look at the analytics, and start to either visually see and determine what's going on your network. The management plane. Every network device, so from our switches to our access points to whatever, any company switches, access points, etc., they need to be able to be controlled by a management plane. Is that okay? It's not the name of a software. There isn't there might be a software called management plane. It's just what happens on this level. The next one down is what we call the control plane. So there, the control plane is where we figure out what's going on around the device, around where that device is situated. What's going on around that? That's what happens on the control plane. And there, of course, you get things like the operating system, right? Every device will have an operating system, just like your phone will have it. And what happens on the control plane? Well, occasionally it needs a firmware update, it needs new software to patch a bug or something like that on the control plane. It discovers the environment. In the activity, when we talk about wireless access points, if you got more than one access point, say you got 2, 3, 4 access points in an office, in a location, in a factory, in a warehouse, then when you switch them on, when the first one comes on, it starts to, to look around. So, do I have any neighbors? Do I have any friends? Then when you switch on the second one, it's like, oh yeah, hey, guess what? I got a friend next door. He lives around the corner. That's his name. When another one comes. So there's this discovery process when they discover each other, kind of like a switch as well. You have switches. If you build a stack, okay, so you connected to him. Okay, cool, I understand. That type of stuff happens on the control planes. Authentications can happen on that control plane as well. Process policies within a management system, Extreme Cloud IQ, you can create policies like those ones I said just now about the 6 and the 5 and the 2.4 gigahertz. You can create policies and you say, this is how I want this access point to actually behave. So you create that on the management plane, but on the control plane is where that policy is actually applied. The control plane talks up to the management plane, says, have you got anything new? Oh, yes, there's a policy. Oh, okay. I'll pull it down from the management plane and I will apply that policy to myself, to that device. And I will now behave in this certain way. Okay. And it almost always, when we ask where does it run, for example, the management plane often runs in the cloud. Certainly in our case, it runs on the cloud. But on the control plane, it most often runs on device or on premises, unless it's SDN, but almost always runs on the actual device, and that device generally is on premises. Management plane, I did say it's almost always in cloud. I need to go back. Not every company is in cloud like us. So it almost always, in our case, runs on cloud. But of course, there are situations where customers might not want it to run on cloud. And so the management plane in that case might then be local to that particular enterprise. So it can run on both. And then finally, the third thing that it does is the data plane. Remember, 3 things that it needs to do is the data plane. So this is the level, the domain, the plane where the actual transit traffic in real time is actually happening, right? So again, if we use the example of the wireless access point, you open up your phone, your tablet, whatever it is, and it looks for devices. It finds the access point that's been sending out the beacons. You connect to it. The control plane does authentication, does all of this bit and bit, whatever it is. When all of that connection is set up, what happens? You start browsing. You go and do some shopping. You go and do this. You go and do that. You go check the football scores. You send emails. You do what you have to do. That's the data plane where the bits and bytes are actually going out, the real-time data. The handling of the radio frequency, again, if you're talking about an access point, if you have a switch, we're not talking in that case of a radio frequency, it's just handling bits and bytes. The data plane is characterized by the fact that it is always on premise, right? Because it's the actual physical device that the things on top are managing, right? It's the actual device. So if it's an access point or if it's one of these, the XR200P, this has to be on-prem. If this is not on-prem, you simply don't have any connection, right? So on the data plane layer, it's always on-prem. And when I say on-prem, I mean it's a physical, it's a physical, device in the environment in which it was designed to operate effectively. So now you should be aware of these three functions. When you hear people talk about control plane, it's like, I get it. I understand where, what happens there, controlling, discovering the environment, processes, policies, things like that. Feel free to take a screenshot. I think we've said already, we don't give out the slides, but you can take screenshots. We don't really mind. Feel free to do that. But when people now talk to you about control and management and data planes, now you know. Remember, very important, the only one that's always on-prem, physical, is the data plane. The others, they are in cloud, or they can be on-prem as well. Important to know. Here, I'm not going to do a massive recap of this at all. It's not necessary to do. If you're at this stage of Academy where you're watching course 4 and you haven't yet done any of the other courses, and when I talk about an OSI model, you kind of go, Aussie model, what is that? The L that they call Aussie or whatever? No. If at this point you're asking yourself, I have no idea what the OSI model is, then you really need to go back to course 1. Just go onto YouTube and you'll find our Extreme Networks YouTube channel. Go look for my beard and my face, all the videos with them. Go look at course 1, and in there I cover the basics of what the OSI model actually is. Very important. In a really short summary, it is a way for us to try and describe how data moves from when you're sending an email, right? You type an email, isaac@extremenetworks.com. When you go tab to go and put in the subject line, that Isaac, that address triggers a protocol in the background that's going to say, where is extremenetworks.com? I mean, computers don't really know. So they have to get an IP address that maps to extremenetworks.com. So while you're typing away the email, in the background, DNS protocol is already going to do a request to find out where is the mail server for extremenetworks.com. Comes back, already puts it, you don't even see it. It all happens in the background. So an OSI model is an attempt to describe what actually happens by the time you get to that where you click on send, what has happened and what is still going to happen to make that email get to the destination that you've sent it to. It's a description. It's not a physical thing. You can't touch an OSI model. You can't, it's not a physical device like this. It's a conceptual attempt to explain how, how data, not just an email, but any data moves within within a network. We have the OSI model and we have the TCP model. They are the same thing. They describe the same thing, but the TCP one kind of says, hey, look at the OSI, the application, the presentation, the session layer. You know what? You could actually just fold them all into one and just call it application. Make it, we like abbreviations in IT. We like this thing. So kind of those three, call it application. Transport, let's keep that name. That makes total sense. The next one, network, let's call it internet, right? Because TCP IP is what the protocol used on the internet. Let's call it internet. Okay, cool. And then it also optimizes the other two, the data link and the physical. It combines them into one and calls network. So it's like tomatoes and tomatoes. Same thing, pronounced differently, describing the same, exactly the same thing. So if you don't know about this, it doesn't mean that you can't do this course, that you're going to get lost as you go through this course. You're not going to get lost, but you will never grow in networking. You will never go to another level in networking if you can't master this. I to be honest with you, I struggled with this, and the reason that I struggled with this is I tried to learn this off by heart. Okay, layer 1 physical layer, layer 2 is this layer, layer 3 that, and I tried to memorize all of these things, and it was a disaster. I'd remember it for 2 days and then I'd forget, and it was only when I really applied myself and really tried to understand what goes on the layers that I then began to understand it. So this is not necessary for the rest of this course, but if you don't understand the OSI, then you should go watch course 1 and understand that. That will really help you. If you can get to, I know it's a little bit, there's a lot of stuff going on here, but it's worth the effort to learn. It really is. That was a single for a 1 minute 20 break so that you can do your, get off your chair, walk around a bit right now. So take the opportunity, get up, stretch, run around, get yourself a glass of water, whatever. We'll be back in just under a minute now. Cheers. Okay, good. Ready to go. Ready to go on. We like to cater for everybody and make sure everybody's so sick and tired of Zoom meetings and stuff. And I know, this is a long training session. It's 2 hours. People have said to us, why don't you do it? Why don't you do it in 7 minutes? YouTube videos can't work unless you do them in 7 minutes. This is not an entertainment thing. This is actually where people really come to learn, right? So we need to make sure that people are fresh and that they, because it's a long time to sit in front of a computer. So layer 2, we're going to be talking about layer 2. When you see an L2 like that in any networking documentation, that stands for layer 2. That OSI model I spoke about, layer 2, that's where we are going to be focusing on now. Now, layer 2 is primarily concerned about local traffic. So we have already discussed in the previous course, course 1, types of networks, and we spoke about LAN. Now, most of you, I'm sure, would have heard LAN, people talking about LAN. LAN, local area network. So if you're sitting in an office right now, chances are you're connected to a LAN. What does that mean? What am I trying to say by that? That you have other people, other devices that are connected together. Okay, that are connected together. Most probably, you will be, if you got a laptop, you are still connected. You just use wireless. So wireless is the connection method that you have. But if you're in a big office, chances are you've got one of those big, photocopier, printer, stapler, coffee maker type, all sorts of fancy, big schmancy thing. If you look at that thing, it is probably, just look around it, it's probably got in the back, there's a network cable that plugs into it, okay, that is connected on the same LAN. If it was on a different LAN, chances are you might not be able to reach it. could be. It could be on a virtual LAN, for example, but you try and get it, it says nope, you can't get it, not allowed to, or can't find it, or whatever. So you understand that local is a local area. That area could be an office, it could be your house. Chances are in your house you have a local area network, right? You got a wireless connect, you got an internet connection coming into your house, and you got a couple of wireless access points in the house. Maybe you got an Xbox or PlayStation, you got a TV, you got one or two other clever little devices, maybe one of those ring things, or maybe a few CCTV cameras. They are all connected in a LAN, a local area network. Now you get WANs and all of those, but that's not really for what we're going to be talking now. When we talk about layer 2, it's talking about communication within a local area network. Okay, local area network. Layer 3 is about something else. It's routing. It's routing outside of that layer of that local area network. But we will get to that. One of the characteristics of layer 2 is, of course, you get very, very low latency. By latency, we mean, the return times. How quick is it? When I say ping, how quick does that ping actually come back? If I echo, how quickly does it come back? If I shout, how quickly does it echo? If to use that as an analogy. But there's also, it has some distinct disadvantages as well. Okay. And broadcast storms are something that we could talk about, and we're going to talk about. That is a particular disadvantage that you could have within a local area network. So we will cover that, and we've already kind of spoken about broadcasts and things like that, so I don't want to focus too much, because I'm assuming you guys have already watched all of that. Basically, when a device needs to connect to another one, it creates a broadcast, and that broadcast needs to be given to every device on the local network. The best way I can describe it is, imagine you go into an office and the office is full. Today, unlikely, right? But I remember, before the pandemic, going into our office in Reading here in the UK, and just like seeing dozens and dozens of people sitting at their desks working away. I don't know, maybe 60 people or whatever in that office. If I wanted to capture their attention, how would I do it? I would have to walk in the door, and then I'd need to shout. I'd need to broadcast, right? Hey, I'm looking for somebody called, Rowan, or I'm looking for a Paul, whatever it might be. And people who would listen to me might turn around. It's like, okay, that's not me. But the person I'm looking for might say, hey, it's me. You need to talk to me? Yeah, I'm looking for Rowan. Okay, there we go. That's the person I'm looking for. Think about the pizza guy. Pizza guy comes into the office. I got a pizza here for John Smith. John Smith, oh, that's me. What's he doing? He's broadcasting. So everybody kind of needs to listen. So if everybody's broadcasting and shouting all the time, it's a little bit messy, right? Well, computers are no different. That's what they do. So that's some of the disadvantages that we talk about. But let's now talk about layer 2 and some of the advantages and the types of stuff that we're talking about. We said scalability and resiliency. Right, Ethernet. This is a term that all of you should be very familiar with. Ethernet. This was invented by a guy called Bob Metcalfe round about, I think it was 1975 is when they first kind of came up with the idea, and I think it was patented a few years later. Bob Metcalfe went on to form a great company, a company called 3Com. Absolutely great company. When I had my own business in South Africa, I used to love selling the equipment because it was rock solid. It absolutely just worked. But that was Bob Metcalfe. That was about, not in my head, I'm saying Bob Geldof. That was about 1975. So that's 25, that's 25, 35, 45. It's 46 years ago. 46 years ago in IT terms is an absolute eternity, right? 46 years. That's an absolute eternity. But today, Ethernet is still the de facto standard for data networks. If a new building goes up in your city, in your town, in your village, if they put new buildings in, believe me, they will be running Ethernet cables in that building today. 20 years ago, they were still putting in Ethernet networks. They still do that today. So Ethernet has evolved, and essentially we know about things like connectors. They call them those little plugs. They have like a little clip on the end, and you push them into a switch, and when you push them in, they go click. And you kind of know. It's also their biggest weakness, right? Because if that little clip breaks, and I bet you've seen this, you probably got this at home, where that little clip breaks and you're like, oh, I don't feel like, I'll just kind of push it in and then hope that no one moves the cable. Oh, that's big trouble. When one of those things breaks, you're going to get an unreliable connection, and it's going to drive you crazy. Why is this not solid? Why is this network not solid? It's that little thing that just needs to be pulled out 0.5 millimeter for it to stop transmitting and giving you a good clean connection. So RJ45 cable, essentially, it hasn't changed what it looks like. It's the same cable that we had, in terms of visually. Inside, it's changed slightly. They've added shielding to it to prevent interference between those cables, and etc. etc. So it's been able to get better and better, but the RJ45 cable remains the same. The crimping process remains the same. That process has remained exactly the same. So Bob Metcalf, we've got a lot to thank for Ethernet, but it's just the fact that we're using it 46 years afterwards just explains how good this stuff is. And if you want to know why hasn't it been replaced, well, because it's so good. Think about the mouse. How old is the computer mouse? I mean, it's old, right? I mean, this thing has been around absolutely forever, but still, they make millions of these a year. And the other amazing thing is that Ethernet was developed at Xerox PARC. I mean, so many great things in the world were developed, at Xerox. It's amazing what that company gave the world. So it's cheap as well. It's really, really cheap. Of course, we now have fiber, right? And some companies, if they've got the money, they do fiber connections. But it's still significantly more expensive. And if there's a fiber break, it's still more expensive to repair and all of that. So Ethernet is cheap. It's well understood. It's easy to, crimp on those connectors on the end. All of that stuff makes it so good and so popular. When we did the course on wireless, we covered a little bit the IEEE. And we said that the standards that govern wireless are 802.11. Okay, so they fall in the bracket of 802.11. And if you wanted to know everything about Ethernet, well, in the IEEE, if you look at 802.3, then that's where you can find the whole entire standard for Ethernet. Okay, and you can go and just look that up. Go into the I think it's IEEE.org or the IETF.org. I think it's IEEE.org/. If you go 3, it brings up Ethernet. If you go to 11, it brings up wireless and everything related to that. So we say that Ethernet is I have to read this because I can never remember this, is a carrier sense multiple access with collision detection CSMA CD technology, right? So the CSMA is just the abbreviation, carrier sense multiple access. It's a common bus technology. When we refer to bus topology rather, it means that you can have one or many devices that have an Ethernet cable or interface can connect to. It can be represented as a single cable or the technology within a networking device, such as a hub or a switch, regardless. But it's a bus technology. So if you have multiple computers, in an office, they all have individual network cables. Those connect all to a common device like a switch, and inside there this port will connect to that port, so that you could go out from coming in on port 1 and go out to someone else who's connected to port 21 or 22. That's kind of the things that we have over there. Now this carrier sense, this means the carrier sense for a carrier sense multiple access and collision. So if we break that down, right, carrier sense, they can sense when there's no noise and they are able to transmit, right, the Ethernet cards, the computers that need to connect on the network. We then talk about multiple access which means you could have multiple devices doing connecting, right? It's not just one. You can have multiple devices, but also with a collision detection. So in today's world, the switch technology nowadays reduces a lot of this collision detection. So people have said to me, so why do you talk about collision detection? Why is it a big deal? I mean, if the switches today are really smart in the way that they send data around and they reduce collisions, well, we have to talk about that, because wireless technology doesn't have an ability to detect collisions, right? So when it needs to connect to something, it needs to broadcast. And there's no ways to detect these broadcasts, so everybody needs to hear, right? So there's this concept that even the wired technology, we've been able to reduce a lot of the broadcasts and things like that just by being smart the way you send packets around the network. With wireless, it's not there. So this is fundamental, and it's important for us to know. I have a little clip. There's a show on UK telly that's really quite funny. And you have somebody who's a host, and then you have three people on each side competing against each other, and the host will come up with a particular topic, and you will be told a topic, and you just then have to create a speech on the fly, or just a short couple of words on the fly. And when I've watched this before, I thought that's exactly how a network works. I've only got about 10 seconds of it, but I'd like to show you. Claire, if you just line that up, yeah, I'll tell you where to go. Just watch this. So a topic has come up. They need to talk on the topic that you see behind them, and I think it's like things that you wouldn't say at a police station or something today, or you wouldn't hear at a police station. And these 6 people on there, they need to walk to the microphone. Look what happens. One of them starts walking to the microphone, and you'll see this woman walk towards it as well. When he sees her walking, he steps away. And that to me is just like, oh, that's such a fantastic example of this collision detection, multiple access. He gets on there and he sees somebody's already, and he walks away. And then this woman can stand in front of the microphone and tell us what she needs to tell us. I know it's silly, but watch this and just see this example. Watch it many times over if you want on video demand, or you can go watch it on YouTube and look at this, and you will understand what this means. Let's play that. Claire, yeah, go for it.
Don't just book it, Thomas Cook it. Dignitas in Switzerland.
Yeah, it's just like, that's the visualization of what I'm trying to explain to you. Okay. in the module, or in the series that I did in one, we looked at quite a bit of detail at protocols, and we looked at frames and how these frames are made up. Here, look at an Ethernet frame. I'm going to use my mouse to show you over here. In the 802.3 frame, it looks something like this, right? The preamble, the destination address, where are you going to, the source address, where is it coming from, the length of the Ethernet frame, how much is inside there, then a description of how much the length, then the data payload. Okay, what is it? Well, if it's an email, it's text. If it's a little video clip you're sending somebody, well, that's a video clip that needs to go. And then there's a check at the end to make sure that when it gets to the other side, they can use that to ensure that nothing went out of sync, that nothing was messed with, no frames, no bits, no data was actually lost, like a check to check some on there. So you can see what an Ethernet frame looks like. Think of it like this. Think of it as an envelope, right? If you write a letter, yeah, I know some people still write letters, but if you write a letter and you need it to go somewhere, you need to put information on there, right? You need to put Mr. You have to put a title in there, Mr. or Mrs., a preamble perhaps. You have to put in a name. In this case, you have to put a destination address. You have to put an address on a letter. You have to put an address. Oftentimes on the back, you can put the source address, where it comes from, so that if it doesn't get to its destination, at least they can send it back to you, right? You don't have to put a length, how long, how long it is. That doesn't work. But you kind of get the idea of a frame. Now, when we talk about a frame, it's like a packet, like an envelope, where you put information inside it, close it, seal it. Maybe you then wrap it in something else. Like when a courier comes, you want to give them an envelope, they put it in a plastic bag or in a brown bag, and they seal it, and then they put it in one of their gray plastic bags, and you can't tear it without damage, you can't open it without damage, and that kind of thing, right? And the data fits inside there. Now, does that apply? Does that mean that you'd have one frame for a letter if you typed an email? No, not. That would be very rare, just to have one frame. You might have an email that might be 5 lines long, and that email might have an attachment on it. So it might be actually broken up into 30 or 40 frames and then put on the wire and send out. So unlike a parcel, if I wanted to send something like this to my mom in South Africa, I'd need to put it in a protective packaging so that it would be able to go out. The same thing often happens with this. You'd have to break it up and then reassemble it on the other side to make it easy to go out, to make it quick to go out. So you take this email, you break it up into a whole lot of frames. All of them will carry the same destination, the same source. They'll have a number on them to reassemble them. When they get to the other side, tuck, 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 they stack them all up again, and there you go. Okay, that's what we talk about when we talk about frames or data packets. That's the type of thing that we're talking about. Now, one of the things that's very important for us to talk about is a MAC address. Now, that doesn't have anything to do with Mac, the manufacturer, Apple. It's got nothing to do with that at all. A MAC address is also referred to as a physical address. I like to think of it, I was going to say a passport, but that's not really true, because when you get a new passport, it has a validity period, 5 years, for example. After that, you have to get issued another passport. But when you do get issued with another passport, your passport number is different to the original one. But if you have an ID card, especially if you're in Europe and you have an ID card, that number never changes. It always stays the same. So passport changes, but ID number doesn't change. Think of that maybe as your tax number. That always stays the same. Now, every network device that you can imagine, from your watch to your TV to your Xbox to something like this, all of these devices, if they need to be connected to a network, they have to have a physical address. It's called the MAC address. And I'm going to call it up here. If you just look just above my finger, my finger's got like where it says the model number. Look just above there, and you're going to see a barcode. I hope you can see it. You're going to see a barcode. And then just above that barcode is a MAC address. Is it just, oh, sorry, just below the barcode is an actual address. And that's made up of 12 digits, okay? Sometimes you see it like in this one, you see it written just as 12 digits. Other times you will see it written as 2 digits with a colon, 2 digits with a colon, 2 digits with a colon, and you'll see 6 of those pairs, if you want to call them, like that. That is a 6 octet value. Now, in binary, an octet is what we call a byte. It's another word for it, a fancy word for it. Octet meaning 8. So octet 8, a byte made up of 8 bits. So if you have 1, 2, 3, 4, 5, 6, if you have 6 octets, that's 6 bytes. 8 times 6 is 48 bits. So 48 bits, okay? But I've just told you that it's actually 12. It's made up of 12 numbers. The reason for that, and the reason why you sometimes see it written just as 12 numbers or 2 numbers with a colon, 2 numbers with a colon, 2 numbers with a colon, is because we don't write that as binary. Imagine if they wrote the MAC address, okay, in binary. Imagine what it would look like. You'd have to type in 48 numbers, and somebody said to you, oh, just give us the MAC address, please. You'd have to go like 001101111. Stop. Was it how many zeros were there? Were there 2? Stop. Was that a 0 after the third, or was it a? Can you imagine how many times you'd have to read it out? So what they do is they convert the binary into hexadecimal. Now, that was the signal for us to take our 10-minute break, our halftime interval. So we're going to do that. And then when we come back, I'll spend a few minutes going over hex, because people have asked me this previously. It's like, can you explain hexadecimal? They're like, oh, we haven't really had a course really to explain it. I don't want to take up a lot of time on it. But if you understand what it is, then when you look at a MAC address, you will understand exactly what it means. So let's take that break. We break for 10 minutes now. 10 minutes, you go out, you stretch, you go grab yourself something to eat, a cup of coffee or whatever it is. We'll see you back in 10 minutes.
is the biggest responsibility for a leader? That is to give the market a vision. Tell the market what is happening, how it is happening, help them wrap their minds around them, and then guide them through that journey. And that starts with the customer. So let's spend a moment in the minds of these customers, whoever they are, whichever industry, whatever level, from a network admin to a CXO, they all are trying to grapple with this post-pandemic world. A world that has fundamentally changed. Why? Because the needs of the people have changed. You, me, all of us, we are living lives differently. We shop differently. We go to school or educate differently. We get healthcare differently. We go and get services from our government differently. We live differently. And therefore, every business out there must change to cater to this demands, this change in demands. And what are they grappling with today? Whoever you are, you're thinking, well, now I need to reach my customers, my patients, my students, my workers. I need to reach them wherever they are. I need to make sure that I can provide them experience wherever they are, which is very similar to if they were in the office or in the hospital, in the clinic, in the school, in an office. That is what is top of the mind. And you're thinking, how do I do this? How do I scale? Not just scale my network, but scale my team, scale my talent, scale my processes. This is the context. This is the surroundings in which a leader like Extreme has to come forward, give a vision, and then show the path. But guess what? These are not the only things that are challenging the customer, because there are other things that have always been there. For example, there always been too much technology, which is too confusing. A lot of customers essentially say that, yeah, you show me a slide, if I could magically switch to that slide tomorrow, everything would be great, but I can't do that. Why? Because I have my own constraints in people, in time, in talent. And then eventually the quintessential question, is it all safe? So what are we doing as leaders? We, first of all, give our commitment, always have, always will, to our customers that we are reducing complexity. We will give them solutions that bring them to their outcomes in their way, at their pace, and we deliver trust. But in this post-pandemic world, the vision to help wrap our minds around it, help their minds wrap around the situation, that vision is the vision of Infinite Enterprise. 3 outcomes that all of us need to deliver. Number 1, we have to be consumer-centric. Why? Because whoever we are, our consumers are changing, therefore we have to change. And we have to learn why they're changing, what their change requirements are, and act on that. The second is our users, our consumers, our customers, they're all distributed. Our students, our patients, they're distributed. So we need to reach that level of distribution. We need to make our enterprises infinitely distributed, and we have to do it at scale, not just the scale of the network, but scale of the team, scale of the talent, and so forth. Now, this whole thing is our vision and our commitment. And yes, there are others who are saying something similar or some portions of it. But once you have something to say crisply and then deliver it with proof points, that's what makes you the leader. So this Infinite Enterprise, while it is a journey towards their outcomes for our customer, this is our North Star. Every investment that we make, everything that we do, every new resource that we bring in, it is meant towards that North Star.
Okay, so before the break, we just got on to MAC addresses, and now we were starting to talk about hexadecimal. And I said to you, I've had quite a few approaches, people saying, I get binary from your explanation in course 1, but hexadecimal, I'm not too sure. Can you explain it? I said, yeah, this is a good opportunity. I don't want to spend a ton of time on it, but it's still a good opportunity for us to look at this. Okay, I'm going to use this example that I've put on here. This here is of course totally fictitious, but we said that the MAC address is 12 digits long. We used the term 12 digits, and we said that is made up of 6 bytes or 6 octets. Remember, an octet is 8, so it's just another fancy word for a byte. A byte is made up of 8 bits, but an octet is another terminology. 8 means 8. So we have 8 bits make up 1 byte or an octet, and we say octet. Yeah, okay. And so we said that 6 of these make up a MAC address. Right. So imagine this device that I showed you. Imagine if they had to write the MAC address in binary. Okay? It would be just nonsensical, absolutely nonsensical. Imagine that someone saying to you, just give me the MAC address, and you're going 0111011. Let's start it. You'd never get to the end of that. And how do you fit in a MAC address that's this large if you write it in binary? Okay, so if you can't write it in binary, then you have to find a more efficient way to actually write that number. And so hexadecimal is that attempt to take binary and actually make it a quarter of the size. Okay, take a quarter. So here we have 88888. That's 48 bits. Really, we should try and bring this down to 24 would be half, and 12. Right, so 12, we now figured out, there we go, there's our 12 from the MAC address. So it's a quarter. That's a huge reduction, right? To help us talk about numbers in a way that humans can understand. You see, computers got no problem with zeros and ones. Doesn't matter how long you make them. But for us as humans, it's just doesn't make sense. So hex is an attempt to do that, and it does it by shrinking down the amount of numbers that we need to 12 from 48. So that's okay. So let me ask you a question. This number here that you see on the screen, that's a binary number. What does that represent in decimal? You guys are so slow. Come on. All right. We know that this value here is 128. That's 64. That's 32, 16, 8, 4, 2, 1. So what does this number represent? Well, it represents 16 plus 8 plus 4 plus 2 plus 1. And what is that? 16 plus 8, that's 24. Plus 4 is 28, plus 2 is 30, plus 1 equals 31. So this number over here is actually 31 in decimal. 31 in decimal. Now remember, binary is base what? Base 1. Okay? So every time it gets to 1, it goes 0, 1. Oh, back to 0, 1, back to 0, back to 0. Right? Decimal is what? Base 10. Right? Every time we get to 10, we start again. Right? Get to 10, start again. Our calendars, base 12. Seconds, base 60. Kind of, makes sense. So hexadecimal is base what? Come on. Base 16. Hexadecimal is base 16. Okay. So the question now is 31 in hexadecimal looks like what? Well, to work that out, first we've got to look at this number in binary. And now we've kind of worked it out in binary. This is 0001111. Right, what I'm going to do here is I am going to draw a little red line down the middle, like that. And I'm just going to split these in half. Okay, stay with me. This is a little shortcut. This is the way that that I found that helps me. Now, you might have another way, and that's absolutely okay. There's no problem. Many ways to skin a cat. So I'm going to show you the way that I use to work this out. By the way, there are many ways to write MAC addresses. So sometimes you'll see them written like this, as a number with 12 digits in them, right? So there will be something like 6A011 BF. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 4 more. F, let's say 3, 3, something like that. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, one more. And let's say C. Sometimes you'll see it written like this. Other times you'll see it written with colons. Oops, I have to undo that. It's not, the colon is not there. The colon is, oh man, this app. The colon is after the second. Okay, so sometimes you'll see it written like this, right? Other times you'll see it written with hyphens. So they'll go 6A hyphens 01 hyphens 17 hyphens BF. You get the drift, right? They'll just separate it like it. So there's different ways that you can actually write a hexadecimal number. Okay. The other thing I wanted to tell you is that oftentimes you will see something like this. You will see on a hexadecimal number, you will see this. And then you will see, you know, like say 6A or something to that effect. This over here, the Z, the 0x, that is just there to tell you as a human that I am now going to talk about a hexadecimal number. Okay? In decimal, we don't have to do that because our lives are in decimal. Our time is, in 60s. We don't really, do anything about it. But to indicate that we're talking about hexadecimal, we put the 0x. And that's very important because you could have 0x and you could have something like 9. Actually, you could have, 1, 1. And you'd think that that is 11. But it's not 11 because the author told you before the number 0x, meaning, this is hexadecimal. Okay, so when you see that, you know what it is. You won't generally find that on MAC addresses. So we have this, and we're talking now specifically about how we convert this into hexadecimal. So we go from decimal to binary and then to hexadecimal. So I've divided it down the middle with that red line, and I've said, okay, forget the fact that it's 0, 1, 2, 4, 8, 16. Just imagine that a byte was actually not 8 characters, but just 4. Okay? Just imagine that. Just imagine that. This is how I think about it. You've got a byte. We know it's 8 characters, or 8 digits, but let's just imagine it's not. Let's say that each one of those halves is just 4 characters. So it'll be 1248, 1248. Okay, so let's take the first part. The first part is this section over here. And this section over here is equal to what if this was binary? Well, it's 8 plus 4 which is 12, 14, and that is 15. Okay, so that is 15. Now let's look at this piece here. If we take the same principles and just say this is 1 and this is 0, 0, 0. So this over here, all of these add up to 1. That's what it adds up to, 1. So we got 15 here, and we got, okay, so let's just say we got 1 over there and 15 over there. Okay, now, how do we represent this as binary? Sorry, good. So how do we represent this as hexadecimal? Well, what is hexadecimal? Hexadecimal, base 16, you start at 0, you go 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How do I represent 10 in hexadecimal? Well, an A, like that. And 11 is a B, 12 a C, 13, 14, 15. If I started at 0, that's a total of 16 digits, right? 16 digits. So let's take that first half. This part here, this was 15, value 15 in binary, right? So let me look on my hexadecimal calculator here. Which value is 15? Ah, look, I can use the F, the highest value. I can use F. So that is F. Then I go to this part, right? The first part. And I say, okay, what is 1? This is a value of 1. What is 1 in hex? Well, I go to my calculator and oops, there we go. There's a 1. So it's a 1. I put that on the left because this is on the left, and I put this on the right because I put the F on the right because it's on the right. Now, I've represented this binary number as hexadecimal. Yes, I've represented the number 31 in hexadecimal is 1F. And if I were to write it, I would write it like this, 0 by 1F. That is 32. That is also 0, 0, 0, 1, 1, 1, 1, 1. That's hexadecimal. Really interesting. Really interesting. Now you know how to read hexadecimal. Now you know how to go from decimal to binary to hexadecimal. Easy to see, easy to read, right? Now it's easy for me. Somebody looks and says, can you give me the MAC address of something? And I say, yeah, look, 6A0117BF F3 3C. That's very easy. Certainly much easier than quoting them something that looks like that. So I hope that that's been useful to you, and that you now understand how to do hexadecimal. If this is all blowing your mind, don't worry about it. Just know what it actually is. The MAC address, it's a physical address that never changes. Now, let me just say this. When I say never changes, there are some devices where the MAC address is, in fact, most hardware, almost every hardware device has a hardware address burnt onto it, right? An individual address that's burnt onto that network card or whatever it might be. And generally speaking, most devices don't allow you, or most devices will not allow you to actually go in and change that. But that doesn't mean that you can't change it. There are many, many types of devices that do allow you to go in and change it. And there are times when you do want to go in and change it, and you can. But you would lose certain things, and it could become dangerous to go and mess with them with the MAC address. Now, some of you are sitting there thinking, Oh yeah, but in mobile devices, Apple doesn't, they have a MAC address and then they constantly change it. That is correct. The NSA years ago with Edward Snowden, he found out that the NSA had the ability to track you based on your MAC address, and so Apple jumped in and said, okay, even though your device actually has a physical MAC address, we are going to present a ever-changing MAC address to the outside world so that you then couldn't be tracked. Don't bet your life on it, but generally speaking, that's a huge improvement over what we had before. But most devices on big networks like we talk about, they will have fixed addresses that come from the factories, and you shouldn't go around and change them if possible, and preferably so. Okay, let's get back into MAC addressing. I need to apologize. Claire's just slapped me on the wrist. She said, it's not 32. Right at the end of the hexadecimal explanation, I wrote 0 by 0x 1f equals 32. And Claire said, not 32, it's 31. So I'm sorry, I messed that one up. I made a mistake. I'm so sorry. Sorry, Claire. It happens, right? It happens to all of us. I'd be terrible if I had to do hex for a living, and people going to the moon depended on me. They wouldn't get there. So anyway, I apologize. 1f equals 31, not 32. Okay. So here we are. We were talking about this this MAC address and how necessary it is. Now that we understand what it is, that number, what it means, that fact that it's hexadecimal, etc., what does it actually mean, right? Well, the number is divided into two, right? 24 bits each side. On the left-hand side is what we call the OUI, OUI. If you're French, oui, yes, but that's not what it means in this case. OUI, Organizational Unique Identifier. So every company that produces networking devices will get one from the controlling body, right? They will get one or more. So Apple will have various OUIs. Extreme Networks has various OUIs. Anybody who makes hardware devices will be assigned this OUI number. And you can go to OUI, I think it's called OUIlookup.com. OUIlookup.com. Claire, can you bring it up, or just put it in the chat? Just put it in the chat window. OUIlookup.com, and you can go there and you can type Extreme Networks, search or go, and it will come back and it will give you all the codes that Extreme Network uses. And just by mapping back to the MAC address, you can identify. If you had no idea who made this device, you look at that MAC address, you look at those first parts over there, and will it identify the organization. The second 24 bits is vendor assigned. What that means is it is the responsibility of Extreme Networks to generate completely random numbers, completely unique random numbers, okay? You really don't want to have duplicates in your MAC address range. It really will cause problems, especially if they happen to be on the same network. It is possible that you could have two separate MAC addresses within two local area networks that are completely disparate, completely disconnected. It can work, but it wouldn't be, advisable. How could you guarantee that they would always be on separate networks, right? So it's something that Extreme Networks will do. Every hardware vendor, they will have software, I'm sure, that will generate these unique numbers so that every device, and I think the combinations they give you something like 16 trillion possible combinations in total of which is it's a bit of, it's a lot of different combinations that you can use. There is a further interesting bit on here. If you look here on the slide, there's this broadcast and local. I just want to kind of open that up a little bit, because if I go here, it explains it a little bit better. You can see that this part over here, the very first octet, okay, if we open it up to the 8 bits, okay, bit 0, the very first bit, you can set to 0 or 1. 0 meaning unicast, means it will be directed to a particular machine, and 1 will be multicast, where broadcast and things like that, will be able to, any broadcast, that this device will respond to that broadcast, which of course is absolutely necessary. And then bit 1 over here is a globally unique or locally administered. So that example where I said that it is possible on some devices to override the MAC address, to put your own MAC address on it. It is possible. But when they ship from factory, they will almost always be set to 0, which is, this is a globally unique number that's on here. If you want to change it, then that bit needs to be changed to 1, or will be changed to 1 to identify, this has been changed by somebody, and this bit now is something else, which identifies that it's administered locally rather than from a global, unique address. I hope that has been enlightening, and that you've learned something. I certainly, teachers, when we prepare to teach, we have to do a lot of reading, and when you start doing reading, you suddenly discover so many things that you didn't know, right? And now that you know. So let's now start getting into design considerations, and let's start looking at layer 2. One of the disadvantages of layer 2 networks. Now, we know the advantages, right? Layer 2, very low latency, quite easy to set up. It's ubiquitous. You find it all over the world. Ethernet, piece of cake. People kind of really understand that, and there's no fancy routing protocols or anything like that. But it opens up itself to some really serious shortcomings. You see, when internet was designed, I don't think that they foresaw all the things and the ways that Ethernet is being used today. So as a result, although it's really cheap and easy to set up and configure, there are really big design flaws in them. Now, those flaws have been fixed by patching it with different protocols to do different things. And one of those patching mechanisms is the loop avoidance family of protocols. Loop avoidance, because this is really easy for you to do if you are not careful when you design a network. So this is really fundamental to designing large networks. Take a look at this network that we have on screen now. Again, for the next few minutes that we share together, I'm going to be looking at the camera and teaching this way, but you're also going to see me looking down at the screen, at the tablet in front of me, because I kind of need this to describe what I'm doing, and it's going to help you. So look at this over here, right? We've got these two stacks of switches that are set up, and you can see that blue connection and that red connection, right? The switches are set up to have redundancy. You want to, in an enterprise environment, in an enterprise where you you just can't go down. Connections cannot go down. You have to have these systems up. We have to have redundancy. Now, in servers, you would have redundancy by having multiple power supplies, for example, multiple network cards, those types of things. On switches, especially core and high-end switches, you'd have exactly the same thing. Multiple power supplies on the back, and then you'd have multiple loops between those switches. So although the idea is to have redundancy so that if one goes down, the other one, just can function and not kill everybody on the network or kill the network. That's crazy to say. It's in this linking of creating this redundancy where you can get bitten really, really hard. Now, if you have a computer over here, you'll see it's got the green arrow. If it needs to talk to, say, a printer or to another computer somewhere on the network, it needs to communicate to a switch. If it has no idea where that printer is or that computer is, it needs to send out a broadcast packet saying, anybody know I'm looking for such and such a computer or such and such a person? Anybody know where they are? Now, what generally should happen is everybody that isn't that particular one person or computer or device that you're looking for should ignore and shouldn't say anything, shouldn't answer. And only the computer that is the one that you're looking for, that has the IP address that you're looking for, that one should come back and say, hey, it's me. That's kind of how it should work. But look what happens when it sends that packet, hey, I'm looking for this. Well, this bunch of switches, 3 of them are going to be getting that announcement. And of course, because it's looped across, this bunch as well is also going to get that broadcast. And of course, once they get it, they're going to send it down, to that switch. And of course, this switch would have already received it from there, or received the packet from there. Then here it would broadcast, and then this would broadcast, and that would broadcast. And you can see, how many broadcasts are going to be happening with something like this. Now, a loop is in a broadcast domain, and when we talk about Ethernet and stuff, we're talking about the broadcast domain. It could easily form this loop, and a loop in a broadcast domain will make the broadcast traffic, unknown unicast, and multicast traffic, which is normally abbreviated BUM, right? Continuously loop around all the connected switch ports. And it grows into this feedback loop, which just continually, goes on and on and on. And we call that a broadcast storm. Now, in the next slide, I have an animation that's showing you, what actually happens. But before we get there, I want to just ask Claire to play the audio that I pulled off a video on the internet, which is the best way that I can explain what a broadcast storm would be, what a loop, the result of a loop on a network, right? If you in a company where there's a loop going on in your network, how would you experience? Would you see it? Yes, to a certain extent, because your network would be really slow. Could you hear it? Maybe people swearing or something like that. But I want to show you, I want you to hear what the equivalent of a broadcast storm is if you could hear a broadcast storm. Okay? Listen to this. We're only going to play like 10 seconds, 12 seconds. Claire? Yeah. We don't need to go all the way. Just say 10, 12 seconds. I think that should be enough. Listen to this. Don't turn up your volume massively loud, but listen to this. Yeah. You get it, right? It's really irritating. In the end, I had to kind of, it's too much, and put my hands on my ears. Like, please stop. That's just too much, right? That's the point. Think about that as a broadcast storm. When somebody now talks about a broadcast storm, now you know what it is. You can see what it is because it's slow. Now you know, you can hear what a broadcast storm does, what it does to a network. It's the same as a feedback loop does to your ears. Okay, now let's look at an example over here. I'm going to, for this purpose, I'm going to call this switch A, switch B, switch C, and let's just call that switch, oh no, that's not going to work. Let's just call it, let's put an S there, SW, S, okay, that works. So in this example over here, what we're trying to do is the following. Computer A needs to talk to computer B, right? It has a packet of information, a frame of information that it needs to send to computer B. How does it do that? Well, it uses the Ethernet cable that it's got. Now, if you're sitting there saying, yeah, but I'm not connected via Ethernet, I'm using, a network, I'm using a wireless card. Yeah, in wireless, the physical medium is the antenna, right? It's not physically connected, but it's that antenna, it's the radio that makes that connection. So ultimately, it's the same process, the same thing. So this one here wants to communicate with computer B, and it sends that information. Now, it doesn't know how to get to B, right? It doesn't know B's address. Now, if you don't know this, computers need to talk to each other on a local area network using MAC addresses. So it needs to talk, but it doesn't know the MAC address. So to do that, it needs to shout, right? It needs to create a broadcast and say, hey, I'm looking for the owner of the IP address such and such. Can you please tell me your MAC address? Because I need that to connect to you. So great. It goes to switch A on port 1. And I'm just using that. It could be port 20. It could be port 15. It doesn't really matter. But in this case, it is port 1. It needs to connect on port 1. So gets to the switch. The switch doesn't know the answer, so it needs to flood that request out on all the ports other than the port that it came in on. So in this case, computer A connected to it on port 1. There you go. So it will flood all the other ports. Just think about flooding, pouring a bucket of water, and all those holes in the switch, that's where the water goes out, right? So it needs to flood all the ports with this request. Fantastic. But guess what? SA is connected to SC down the bottom over here. And it's connected via port 3 on that switch. And so it floods. When that bucket of water goes, well, what happens? It flows down that way. Guess what? It is connected to SB via port 2. So the flood means that it goes that way as well, right? And when it gets over here, okay, it knows, computer A has got this MAC address because it's the source, source address, IP plus the MAC. It knows that information. Great. Now, here, guess what? It's got one port that is connected to SD, that switch D. What happens then? Well, if you pour water into the switch, no, please don't go and pour water. It's just an example, right? It's going to go down there and it's going to hit this switch and it's going to do the same thing. Broadcast, hey, I'm looking for this IP address. I'm looking for the MAC address for this computer's address, IP address. And this one, of course, is going to do the same thing. It's also going to send that information. It's going to send that information through. So you're going to end up like this. You're going to end up with all these packets arriving at computer B, right? They all arrive at computer B, maybe at the same time, maybe a millisecond after each other. This creates a problem because computer B needs to respond to this. But what happens is these guys over here, they don't sit back. They don't send one broadcast and then just wait, like, let me do some, let me varnish my nails, let me polish my nails, and I'll wait for that response to come back. Yeah, that could be. They don't do that. They just keep flooding all the time. So this switch is flooding constantly. This switch is also flooding. This one, and they are continually flooding. And look at what happens to this computer over here. This computer over here is desperately trying to answer, but every time it starts, another packet comes in, another packet comes in, another packet comes in, and of course, what does it need to do? It needs to decapsulate the pack, needs to look inside, just as it finishes that, another one comes, and then another one comes, and another one, and another one, and these things, they go into a loop. A continual loop. They just keep looping all the time. Hey, does anybody know what the MAC address is for this IP? Does anybody? And this pure guy over here, he can't get his answer out. He can't because he is so busy. Now, in the old days, this computer, 20 years ago, this computer might die, might just like, I've had enough. Nowadays, they got processing power, so they can handle it. But what happens on the network? These links, okay, that you had 100 megabit links or whatever it was, start to suffer because there's just constant amount of traffic, looping. And eventually, the ports, these ports over here, this port over here, this port over here, they simply just go red, and they're like, we can't handle anymore. What happens? Imagine you have another computer that's connected to here, right? Well, the computer's working because this guy is not the right guy. So he's just supposed to ignore the packets. But what happens is he's just been hit by packets, constant packets. So the computer continues working, but the network grinds to an absolute standstill. And then it's like, this network is rubbish, it doesn't work, and whatever. Why? Why is that? Simply because of these loops, the amount of packets. We're not talking about, 10 packets in a second. We could be talking about, if this is a large network, hundreds of thousands of packets per second that is now being sent because they're all broadcasting. Remember, they broadcast. And so this poor guy, if he eventually manages to get that answer, it's me, what happens? Because these links are so over capacity, because this port says I can't anymore, it never goes anywhere. Layer 2 loops. Layer 2 loops. You can see the problem, right? You can see the problem. Now, computers also have, or switches also have, MAC address tables in them. So look at this over here. When it started off, it said, this packet is, this IP address is that connected to that MAC address, and that's coming from computer A. So the switch has a MAC address table. In fact, all of these switches have MAC address tables in them, which they use to map an IP address to a MAC address, okay? But what happens? When it first went out, port 1 was A. Now, because of these loops, it's not port 1 anymore. It's port 2. Port 2 is A, because the packet is looping and the MAC address table says, oh, sorry, it's not port, it's port 2. Port 2 is A. Port 2 is A. Port 2 is A. What happens? A minute later, I should have cleaned that up, but you can see over there, port 3 is now, no, I'm A. No, port 3 is A. And this MAC address table is changing as well constantly. And it's not only doing that on one of those switches, all of the switches are doing the same thing. They are updating their MAC tables. So not only are they looping, the MAC tables are being constantly updated. We call that instability. So you have MAC table instability, you have replicated frame, you have link congestion. In other words, you pretty much in the shtuk, right? You are pretty much in the shtuk, and your network is grinding down to a halt, and your phone starts to ring off the hook, right? At that point, you know there's a little bit of trouble coming. Why? Because you made a mistake when you designed the network, or the switches, you didn't set up a protocol to prevent that from happening. So in layer 2 networks, even though they have all of these advantages, they also have some serious disadvantages, and this being the most serious of all. So if you can solve this, we can do great things with layer 2 networks. And there are multiple protocols that have been invented. The most popular and widely used of those is the SLP, right? SLP, Spanning Tree Protocol. Even Extreme has got its own one, ELRP, Extreme Loop Recovery Protocol. And the idea is behind those is you try and break that link that's causing this loop. That's what you try and do. And the way you do it is by having one switch be, we call it the root, okay? We call it the root. Some people refer to it as the center of your network. Now, generally, as an IT person, you shouldn't accept when you get switches, just use that bridge ID. Okay, so the bridge ID is a combination of MAC address and other information. Now, if you leave that as default, which none of you do, right, because you're all engineers, if you leave that as default, then what could happen is your oldest switch that you've got in that network will automatically become the bridge, right? Because the way that the numbers are concatenated and put together means that the first part of the number could be the lowest number, therefore the oldest switch. So as a good network engineer, you're not going to allow that to happen. When you bring up the switch, you're going to configure it, and the one that you want to be the root, you're going to give it a low bridge number. So that means it now becomes the bridge. And once that has been designated as a bridge, then each switch is going to calculate its route to that route, and it will do it by using a cost mechanism. And when I say cost, it's not dollars, it's just an arbitrary number. And you could say, well, if I need to go to London from this way, from Cambridge to London, if I go this way, the cost is going to be, say, 80 miles, could be time, could be whatever. If I go this way, then the cost is something else completely. So it will look and find what is the lowest cost, and then use that as becomes a forwarding port. And in that scenario, what will happen is that the port that's causing the loop will no longer function, will no longer talk and pass that traffic through. And if that is the case, then all of these are forwarding ports. So that request comes through to the switch on port 1. It passes it down. It passes it this way. It passes it this way. It passes it this way. But there is nothing going from here to here, right? So how many packets does it get? How many broadcasts does it get? It only gets, boom, this one. It can easily handle that and respond, and it goes back. And now computer A knows the IP address, knows the MAC address. Thank you very much. I can send the packet and it works. Isn't that brilliant? Isn't that brilliant? But there's a lot to unpack. If you want to unpack, spanning tree protocol, there's an enormous amount to learn. It is so interesting. So I suggest after the lesson, whatever, make this your homework. Go and look up STP. Go and look up Spanning Tree Protocol. There's many good teachers. There's some stuff that's really, really complicated, or when I say complicated, they go into the smallest of detail, and there's other stuff that you can, in 3 steps, this is how you do it. Go and look in that. Go and look for some of those. Watch those, because it's so interesting when you understand how this works to solve so many other issues. Right. Thank you for watching. I hope that you've learned something today, even if it's just hexadecimal. But I hope it's been much more than that. I hope you found it enjoyable. Thank you for watching. Thank you for participating, for answering questions, for asking the questions. It's fantastic. We love this interactivity. Don't forget Discord. I'll see you next week. Cheers.